Next topic we'll talk about is strain. And again, this is not really that big of a topic. I mean, it's a big topic, but it's not like you're going to be doing a lot of problems where you're calculating the strain. You might have a problem or so that you do, or a couple, but I mean, by far and away, stress was this really, really big concept. You're going to be doing a lot of work with that. Strain, though, you need to know what it is because it's analogous in a lot of ways to stress. Okay? Stress was force per unit area. Okay? Strain, if I give you the definition of that, it's going to be the deformation per unit length. Again, another way to say that is a lot of people like to say, instead of deformation, they say change of length. Over, and instead of unit length, they're going to say original length. Okay? So if you hear people say deformation, that's the same thing as change in length. If you hear people say unit length, a lot of times they're talking about original length. Okay? The length of the unit. Okay? Symbol-wise, we use a little Greek letter, sort of looks like an E. It's called an epsilon. For deformation, we usually use a Greek letter that sort of looks like an incomplete figure 8. That's called a delta. That's a lowercase delta. You might be more familiar with the uppercase delta that looks like a triangle. Okay? But for our purposes, our text uses sort of the lowercase. And then for length, original length, we'll just use L. What kind of units do you think I'm going to come up with in strain? Well, how are you going to measure the change in length? What units?
Pound per foot.
The change in length, pounds per foot?
Inches, feet.
Huh?
Inches, feet.
Inches, feet, a unit of length, right? So maybe inches, you're right, inches, feet, probably inches, probably going to be more common for us, but no, you could do it in feet. What about the original length?
Same.
Same.
They're going to cancel each other out.
And they're going, yeah. So dimensionally, strain, for all intents and purposes, is dimensionally null. I mean, it doesn't, everything cancels out. But there are units, inches per inch. All right? I said this in some ways could be sort of analogous to stress because, you know, is the amount of deformation that a material undergoes, is that really enough to tell you what's going on? If I told you a bridge deformed, you know, on a hot summer day, deformed by 2 feet, what would you say? Huh?
Don't go on the bridge.
Don't go on a bridge? Now, what were you going to say? Yeah, a lot of deformation. Okay. What if the bridge was 6 miles long? Would that be a lot of deformation? Yeah. I mean, if the bridge is 100 feet long and it deforms 2 feet, yeah, that's a lot. You know, but that's the deformation is the same. It's 2 feet. So, but the deformation over the length, or per unit length, or original length, is, you know, that's what you got to measure it up against. Okay? So strain, you know, we always said stress is equal to load. I didn't want you to get that worked up over load, thinking, man, it's 1,000,000 pounds, what are we going to do? Because 1,000,000 pounds might be easily resisted depending on your area and your material. Same way with strain. I don't want you to get all worked up about the deformation. You got to look at the deformation in regards to the total length of the member. Okay? So, yeah, and unit-wise, inches per inch, millimeter per millimeter. You can do inches per foot, but that'd be really odd to do it that way. So, I mean, most of the time we have the same units, top and bottom. You're going to end up with a small number. Here's why you're going to end up with a small number. When you really think about this, if I had like a member, let's just go back to a column. And I told you the column was 110 feet or 120 inches in length. And I pressed on this with some load, and that load caused a deformation of 1/10 of an inch, which you might say, man, you know, if the column actually shrank 1/10 of an inch, it's pretty amazing, you know. But the strain in that would only be 1/10 of an inch of deformation divided by the original length, 120 inches. And so the number, the strain value is going to come up, what?
It's another 0.
0.30 is what?
8.3.
8.3 inches per inch. So it's a small number again, but don't get fooled by that, because you know I gotta have a small strain, you know, and again if my member or structure is real large, I gotta have a really big deformation that I gotta handle somewhat. What I really need you to understand is what does that 0.00083 mean? Well, what it means is if you originally had sliced this column up into 120 1-inch segments, the amount of deformation per those 1-inch segments would be that much. So each 1-inch segment is deforming that amount. That's what the strain is. If I add all those the deformations of all those 1-inch segments up, what does it come out to be? 0.1. Sort of the same way that we talked about stress and the rope. You know, if you add up all the forces on those little strands, what did it come up to be? It came up to be the total load. You add up all the little incremental deformations over these incremental pieces, what does it come up to be? It comes up to be deformation. Yeah.
Now, since the units are inches over inch, do you demonstrate that way, or do you just leave the units off?
I mean, I usually put them on. I mean, as you use this, like in your problems, like we'll, not today, but we'll talk about this in another class, as you start using maybe units of strain, this just sort of becomes null. I mean, there's inches over inches, everything cancels. But so in those problems, your units are going to be based on whatever else you're multiplying it by. Okay?